So let's see what's up next on my slides. Ah, yes. Now we're shifting gears somewhat, because domain-specific languages are in some ways a craze now, because for machine learning, domain-specific languages has been seen as sort of the way forward, because it's very limited what you can do in machine learning, and then basically you have this API towards the primitive machine learning algorithms. And we saw that for the graph library. They want to build up a library of useful graph BLAS abstractions, which you can use for the higher levels programming of your domain. And I suggest that we then link in our template requirements to those higher levels, so we can replace the basic implementation on a per-case basis. But this is sort of approaching the sphere of domain-specific languages, which has been sort of hyped quite a long time as a solution to the problem of how to solve problems in a specific domain. So that's sort of coming up with a computer language for a specific domain. What we are dealing with here are domain-specific programming languages, because we are trying to solve programming problems. And sort of the benefits are that you have concepts matching problem domain, easy to develop solutions with appropriate concepts, tool support, which knows the DSL, can take advantage of properties of the DSL to make more efficient code. The downside, of course, is that if you're building tools to reap the benefits of the domain-specific language, you have to develop those tools, you have to maintain them. And then suddenly, unless it's a heavily used domain like machine learning, it's going to be expensive having your own suite of tools to solve your particle problem. And also when people come up with a DSL, they're very interested in the physics of the domain, and they don't ever think about how to organize a large piece of software for that domain-specific language. So you don't get object orientation, you don't get modules, you don't get templates. Here's the domain-specific language. It's great at this. And if you start building too large programs, well, it's your problem that things are getting out of hand. But let's see. Because there's an interesting connect now between domain-specific languages and what we are doing. Because when we define a requirement, we are basically defining a specific sub-language for the domain where we intend to write our templates. So the body of the template is in the domain-specific language defined by the requirement. Again, this is something we get with type-safe generics, type-safe templates, which you don't get with non-type-safe templates. In the type-safe templates, we're checking that the body of the template code belongs to the DSL, belongs to the requirement. So you're sort of getting the benefit that inside the template body, however large or small it is, however many functions you put in there, you are getting something in the domain that you design the requirements for. And we've done some examples of specific requirements for traveling or things like that. So I'll call this an integrated DSL because it's part of, in this case, the Fortran language, and you're using it to your benefit when writing template code. So it's fully integrated in the host language, that's an integrated DSL. You use all tooling that exists for that language already. You can use all abstraction mechanisms that are there, sort of use your derived types, build them in the way you want, use them as arguments, matching the requirements, use them inside your body to build new abstractions. It's all available because you are programming in a full-fledged programming language. You're not limited to whatever was in the DSL, even though you have all the types and all the functions you want. And you can flexibly extend that because the requirements is something you can easily extend if you need more functionality. So there's no tooling overhead in creating this domain-specific language. Create it by writing your requirements. And you get more type safety from your domain-specific language than you get for the regular language. You're talking about mass, you're talking about speed. You're not talking about endless numbers or floating point numbers. So this is sort of getting the benefits of domain-specific languages, and you're getting the benefits of a full-fledged programming language, which sort of supports your DSL by having that type-safe generics. Now this is sort of part of what we've been discussing today. You create the requirements that suit your problem. So if we had been full of energy now, we should have taken a break for an hour, and you should be working on this problem. Because each of you have interesting physics problems or chemistry problems, and sort of we want to figure out the types. We did some sort of mock exercises for small problems. Let's really try that for some bigger problem. I don't know if you have the energy for that, but it would have been really fun going around in a classroom full of people trying to figure out what their domain is about. Well, also, if you try to do this, you will see that it's not necessarily manifest in the way you talk about your physics problem, your problem. It's more manifest in the way you think about it. That is because when you talk about it, you're typically being forced to talk in, let's call it a low-level language. So you communicate in the low-level language, but your thinking is in a more abstract language. And that's why what you write in the lower level language is correct. Because if you don't have that understanding of the domain, what you write in the normal communication language is going to be meaningless. And without that same training, nobody's reading your stuff in the communication language because it lacks information, it encodes information in strange ways. But a person with the same training is going to discover the structure behind the encoding and can continue to think at the abstract level. But what I'm sort of promoting is that make those things manifest as entities in your code, and with this cheap domain-specific language approach, write your requirements to capture those ideas. And now I'm not talking about multiplication and addition, I'm talking about the real abstractions in your physical domain. So you think about the types, you try to identify them. Then you try to find the operations in that domain. And again, it's necessarily not how you speak about it. You speak about matrix multiplying, maybe you mean linear transformations. Maybe you mean multilinear transformations. These are different things. These are objects at a different level, but they're just, again, tools in talking about the real physics. So we found a language which is sort of a matrix or array-based language to encode all our problems in, but we're not encoding it in the way the physics is. We're not encoding it in the way the chemistry is. Astronomy is. And another thing is that, and this is something good or bad with object orientation, is that, with pointers and callbacks and stuff, you're hiding information. It sort of makes something simpler at the surface level, but things are hidden. And actually, we can think about these two energy functions. So if I make an energy function with hard-coded mass, that's fine, because I know what it is. If the energy function has a pointer to some object which has the mass, then it gets complicated. Because now I don't have control over what this mass-containing object is. It's somewhere else floating in my program. And somebody who's dealing with something completely different might say, oh, here's a nice variable. I will put some number in it and use that as a temporary variable in this section of the code. And thereby sort of your pointer to this mass variable is messed up with some other data which is not relevant for the problem. So sort of these hidden things which call out, which call back to an owner of some sort, they obscure the information that's involved and they make this kind of analysis more difficult. So this might be better, this is okay, but it's not okay if the implicit mass is supposed to come from somewhere which isn't fixed but may be modified involuntarily by some other part of the program. So pointers are a dangerous thing. More dangerous than we think, perhaps. So make everything explicit, because that turns out to simplify things. Describe the precise intention of all operations in the same way as we should describe the precise intention of the types. Describe all input information needed. Often you sort of omit some because they're easily implied, but make everything explicit. And also make very clear what is the output, what does the output need to be computed. And it's very easy to be confused by words and names. And I see that when I'm writing text, because when I'm writing this part of the paper, a certain terminology is normal. And when I'm writing this part of the paper, another terminology is normal, but it has the same words in both places with different meanings, which makes it very difficult for a student to read the whole text, because they will confuse the use of the same word with the same concept, even though it is two different concepts. So, making everything explicit, trying to separate those cases where you're using the same word for different things and differentiating them somehow. And this happens in every field, because the normal terminology is sort of moving around and the same word may appear in different places and you may get confused because you think it's one function, but it's really two or three different functions you're talking about. And especially if you combine things from two different domains to solve your problem, you're bound to get into trouble because the same word has a different meaning in the two domains. So this is sort of general. Now I would really like you to sort of start working on this, but maybe we should pick that up tomorrow so we have some rest and freshened up. Or are you ready to start on this?
Tomorrow, then maybe also there will be more people back online.
Yeah.
There are 15 left with all the connections out of this room.
Mm-hmm.
So I think we have 3 or 4 connections to the just
Yeah.
so we have probably 12 or something left from outside. And I don't know, we should attempt to do something tomorrow and then somehow involve them in breakout rooms and let them work out maybe. Because then they could also do something.
But maybe I should show my next example so you sort of see how things can be elevated and sort of have a feeling for these more abstract layers. Because this is one thing we did sort of back in the 90s, and that was work on coordinate-free numerics. So now I'm just showing the upper layer of abstraction here, which has to deal with how I formulate PDEs. So it's not for any domain, but it's sort of general for the PDE domain itself. I'll sort of show some type declarations for that domain. some coordinate insensitive basic operations, some contraction operations, and some spatial derivatives. And then we'll look at two PDEs and sketch a third one. So basically, we want to define a DSL or a declaration of requirements that allows us to talk about PDEs. We've been focusing on explicit PDEs, but we also did some work on implicit solvers. And this is not in Fortran, even though it's not very far away. So I got tensors. These are sort of scalar values. These correspond to vectors, but I have covectors and vectors. And the reason I have two of them is that they behave differently under coordinate transformations. And also, if I start separating covectors and vectors, some operations are coordinate sensitive and other operations are coordinate insensitive. When I come to dyadic tensors, which correspond to two-dimensional arrays or matrices, I sort of have two covector components, one covector, one vector components, and two vector components. In certain parts of physics, these are distinguished by having upper indices and lower indices. And the contraction operation is when you have an upper I and a lower I in some position, and you contract because you do a summation over the common I. So physics people have been having the math notation to disambiguate these things because it helps them in their reasoning and the work with the system. And for the problems we've been working with, we have had these dyadic ones, and then we have these sort of 4 indexed arrays, and sort of 3 Cs, 1 V, 2 Cs, 2 Vs, and 1 C EVs. Of course, more combinations are possible. In the system here, we are sort of first giving all the Cs and the Vs. You could also have a system where you sort of say I can have C, a V, a C, a V, but it doesn't add any type safety to what you're doing. So we sort of decided this seems to be the basic types. Throw in more tensors if you need higher, even higher levels of them. I think if you're going to some kinds of electrodynamics, you need 11 components or something like that. So when you go there, just throw in the extra ones you need. So here are some basic functions. So it's a bunch of division, subtraction, multiplications, addition, and this sort of scalar tensor multiplication operations. Now the difference here is that the R is just a real number. This is a scalar tensor, but the scalar tensor could be temperature, a vector temperature. A vector tensor could be the draft, air moving inside this room. And dyadic tensors can talk about some spatial changing property or something like that. So, yeah, we can divide tensors by the scalar component. We can subtract things when they are of the same type. We can add things when they're of the same type. We can multiply scalar tensors with each other. And we get a large vocabulary of these operations here. And so that sort of sets basic things you can do with these multidimensional arrays at the level of PDE computing. Then we need these contraction operations, matrix multiply in many cases, but I need to be careful about how I apply a 2cc tensor to 1v tensor, 2cv tensor to 1v tensor, and then this 1c is consumed by the v, and I reduce the number of dimensions. And here are sort of various versions of c's and v's with dyadic tensors. We are creating new dyadic tensors. This choice here was driven by the example domains I was looking at. So other example domains may have other combinations of functions here. These are coordinate system independent, metric dependence on these operations here, the dot products. They are metric sensitive. And you could change them into metric insensitive operations by first doing a translation between vectors and covectors, and then, or translating from covectors to vectors, because then you would be in this multiplication domain where you are coordinate system independent, but moving between vectors and covectors is sensitive to the coordinate system you have. We've experimented with various kinds of curvilinear systems, cylindrical systems. So choosing these kind of systems is possible to embed in the implementation of these operations. But these operations here on the top, they take care of when you need to apply a metric and when you don't need to apply a metric in the algorithm. So you can use them without worrying about what is my coordinate system. The operations themselves worry about that. The use of them does not worry about choice of coordinate system. Spatial derivatives, gradient and divergence. You can see the gradient increases the vectors components of the data, and divergence consumes it. And dot gradient, I guess that's this is nabla, this is nabla dot, this is dot nabla, and Laplacian is nabla dot nabla. For those who know that notation, which is typical in physics. So physics people have developed a notation which allows you to be aware of these things if you sort of know the deeper reasons for why the notation is like it is. Also, Laplacian is very common, not because it's a primitive operation, it's a combination of gradient and divergence, but it has is numerically better if you implement it directly rather than having this combination of operations. So this is a largish signature, largest requirements listing. You can easily translate this to Fortran. It gets very verbose, so every line here becomes 3 or 4 lines of Fortran. But that's Fortran's fault. It's not the conceptual idea's fault, as you can see here. And then we can write 2 solvers. So this is a single time-stepping function for Berger's equation using an intermediate half step. And you can recognize these operations from the signature that have been type checked. There are some constants thrown in somewhere, like dt is sort of time resolution. Nu is a constant describing the medium that's being worked on, and tensor 1v is the wave, the movement that's, and this sort of Berger's equation is working with. But what you can see now is that things are very close to the physics, and you can sort of translate this into physics notation by inserting nablas, dot products, nabla squared, multiplication with a scalar, and subtraction. So this is sort of basically taking the mathematical formula for a half-step solver for Berger's equation, these 4 lines of code, and just encoding them using function calls in a programming language. Unfortunately, we can do this a bit cooler, because we can define these things as infix operations, prefix operations with sort of dot gradient dot, or how do you call dot period to make it into an inline operator, binary operator. So Fortran has some tricks up its sleeve which would actually make this look even closer to the mathematical formula. Here's an elastic solver, a time step of the elastic solver. So these are sort of the wave of the previous time step, the wave of two time steps ago. This is the output for the next time step. And these are sort of the constants describing the medium where the computational waves are moving. Whether this is a one-dimensional guitar string, it's a 2D plate, or it's a 3D seismic slice of the underground. Of course, 3D seismics is very important in oil exploration. And now it's very important for the mooring of offshore wind farms. Yeah, basically these are the mathematical operators, fairly straightforwardly written from the formula. And on the next slide, I have what the formula would look like. Added a force field here, so the double derivative in time. Well, this is supposed to be the V derivative, I think it's this one. No, this one is the V derivative. This is the elastic wave equation. And you can see that we're just using a few symbols, we're having a few variables of various types. And this is a real simulation based on the software. This is the PDE that describes the elastic wave equation, given that your operators do what they're supposed to be doing. And here's the heat wave. You can see there's the Laplacian. And it's a very simple formula, and again, it's the same operators. So once you have them in your API as a requirement, you can easily just write this in the language of coordinate-free PDE solvers. And then you don't need to worry about the coordinate system at that level. Yes?
So these derivatives are computed numerically, or do you use automatic differentiation?
No, this is numerical. So all of these things are represented as large data structures and functions or procedures working on those data structures. So the derivative would be something that would take the data corresponding to the temperature distribution. This temperature would be a scalar field, and then would create how temperature flows inside such a system. So it's real computation. Yeah?
You said find a difference then, or because I'm still coordinate-free numerics. So now if you have a soft set on a grid, and I will explain Q as a function on the grid and take the derivatives as find differences.
Yes. And we did lots of studies lately on finite difference version of this. But if you look at these 2000 papers, we discussed finite element methods. So things we did, borehole simulations with a cylindrical coordinates and things like that within this framework. Most of the seismic stuff was finite difference, the Bergen stuff was finite difference. So we'll study a little bit tomorrow how we take finite differences and find an array API which sort of gives us the components that we need. So yes, each of these are operations on large arrays or arrays of arrays. So we might need a 3D array to describe the data set, and then we need another 2 dimensions, or another 4 dimensions to describe the operators on those, to describe all the components of the data. So the 3D data set is the room. We need 3 of them to describe how the air is flowing. And for some of the tensor stuff, you might need even more information to describe the elastic properties of the rocks we're looking at. But when we're doing the elastic simulations, it was very easy for us to extend this to sort of from isotropic to non-isotropic materials to poroelastic materials. And at some stage, we had a poroelastic code, which was running on a local supercomputer. There was a consultancy company who actually wanted to buy computation time on that computer to run our codes on their problems. But at that moment, the contract was being signed. There was a downturn in the oil price, so the consultancy company couldn't sell their services to the oil company, and then they didn't buy the contract. But our code was sort of very early in being able to solve poroelastic wave simulations. Because for us, it was just changing a few hundred lines of code to move from elastic to poroelastic. It was the same library, but more variables and more operations to be called, but the same operations to be called in the poroelastic case. So we changed about 100 lines of the entire system, which was actually fairly small. I think like 5,000 to 6,000 lines altogether. Actually published those numbers in some early papers. So sort of changing equation from isotropic elastic to poroelastic was just changing a small fraction of the code because it was written in this high-level language I showed you. At that time, we were using classes and nested layers of stuff. Now I would have had template parameters requirements for the API and just thrown in necessary data structures. Actually, a layered approach to throw in each concept in one layer at a time. But this is sort of saying that, okay, when you think about your problem, these are sort of game problems which fit sort of in high school, I guess. But you can think about real physics, real problems, and stick to your physical operators doing the physical computation. You don't need to transcribe your physical problem to an array problem to solve it. You can keep it at this level, and we can then instantiate that template code with appropriate coordinate systems, with appropriate discretizations, with appropriate parallel distributions, and get that to run. We did this already around the year 2000, and nobody's taken us up on it, which is very disappointing. A few people have sort of discovered coordinate free numerics, and hopefully we'll have a project with Lawrence Berkeley next year. And now I think it becomes more exciting trying to figure out what is the requirements for a templated version of your problem. And the reason it benefits you to go to templated is that you don't have to think about what are my tensors. You just say, I need them. Then you think about what are my tensors after you've thought about how do I write my solver. At this level, not at the array level. I think this is the last slide for today. Now, should I drag this out for another 2 hours, or should we try to finish here?
It's quarter past 5.
Are we over time already?
No, there's a quarter, 15 minutes left. 15
minutes left, okay. So we'll summarize this and you can ask questions. Typeset generics. I've sort of hammered in that this gives us possibilities which are not matched by non-type safe generics. You don't see these examples in sort of C++ environment because they don't have type safe generics. They can't build up these internal DSLs just by declaring requirements, because there's no type safety ensuring that they are staying inside that DSL, that they're using only the things from the requirements. Their approach is that we attach ourselves to the operators in the environment, not that we place everything inside the requirement. So the type safe, the body is written in the DSL, and when you instantiate it, you get no abstraction overhead because you're instantiating it directly to the data that you will be computing on. Unless, of course, you are using some abstraction in between. And the type checker will discover problematic code inside your template and in your instantiation. No megabytes of instantiation problems, normal specific error messages where the error occurs. This is the error inside the body. You used a symbol that wasn't there. You used a function called in the wrong place because you have wrong arguments to it. This is the type of error messages you get from the template body. From the instantiation, they tell you that this function is not binary, this function cannot match up like that. When making all these things explicit, we get surprising reuses, like sort of my linear algebra package is now used to solve graph algorithms. Because the instantiation says that I'm now solving a minimal flow problem on my graphs or something like that. And the graph class people are sort of exhibiting of what we can do with linear algebra as encoding of graph operations. The instantiation occurs no runtime overhead because you don't call into derived types, unpacking and packing an abstraction. You're calling directly into the types you want to use. Okay, well, I'm just saying that what we don't have as of now is the ability to exploit the rewrites that we want to have with the DSL. So that's something we will look into tomorrow and see that we can use that as a tool quite actively. But of course, this is beyond compilers, but not that far. So it's tools that should be integrated somehow with the compiler infrastructure, though it should probably not be part of the compiler itself. And also, when you develop your DSLs, you really need insight and reflection on the domain you're working with. But you sort of get a new perspective on it, and you're forcing yourself to rethink, what am I doing? Why am I doing it? Why haven't I taken my physics background when I'm doing my computations? Why do I end up with all these arrays with indices that I lose track of? And that's basically it. Any questions?
Yes, do you teach this?
Part of it. Of course, this is entirely new. Fortran has never had this before. So this is one of the early seminars on type generics in Fortran.
I'm thinking of that there are many scientists who have no training in Fortran, programming Fortran.
Mm-hmm. No, we don't.
They write code that is not very good.
Oh, no.
It might be efficient because they polish that, but the structures and such is no good. And it's going to be worse because these young students that are going to take up their PhD in a couple of years, they have learned Python since primary school.
Yes, I'm getting worried. Really worried, because I also see that now in CS education, that with a Python background, there's so many concepts they don't know, like type checking is sort of out of the window. Python works extremely well on the small exercises they have in the beginning courses, but how do they scale it up? They don't have the cannons anymore. They just have sort of the traps for the small birds. And that's going to be a problem, but it's very difficult to convince the whole system that we need to bring back the cannons, which are improper for the two problems they're solving, but which are preparing them for the big problems they will meet later. So yeah, the popularity of Python, I think, is undermining the quality of our education. And I don't think the system is aware of that.
I think it's twofold. It's
Mhm.
bad for those people you address now, but it's good for those people who only will write simple scripts that do some sensible work that will fit on a laptop, write in 5 minutes and do some data analysis that will take a month to do on a spreadsheet. So for that Python is good, and for those people is good, but for the computing professionals, the HPC, I agree with you, it's bad.
It's also bad for those who are going to build our systems that we use in society, the administrative system for the tax office and things like that. Because those systems are not going to be like a 10-line script. They're going to be massive systems. And if you can't trust those systems, you have a problem. And if our students don't get the tools to help them ensure the safety, not external safety, but sort of the internal consistency of that piece of software, things are going to sort of smolder up. We've had for decades sort of how to improve the quality of internal things, and now we sort of change that to sort of Python is very good for the introductory course because the learning outcomes of the introductory course matches perfectly what you can do with Python. But it doesn't help for the advanced courses coming later. Yes.
So do you have any comments about the Julia?
I haven't really looked closely at Julia, but it seems to be nice in many ways, but they don't have a good template system.
They have.
They do not. They built, when I looked, they built that on Java's interface system, that has many downsides because you need to decide the interfaces a priori, which means when you get your physics problem, you cannot use the standard library because the standard library did not match your DSL. And sort of that, you need sort of the freedom you get in C++ to match your problem to the way you want to code, but then you don't have the type safety. So here, Fortran delivers or will deliver type safety in a template system, which is very flexible. So yeah, Julia is definitely an improvement over Python, and it has a very nice infrastructure around it. This idea of sort of literate programming, making things available on the web, you can run them and see the effects of the code. It's very nice to getting started. And I haven't looked at sort of the large scales use of Julia, but I think it sort of matches Java in many aspects, and Java is okay. So I wouldn't dismiss Julia, but if every language without type-safe generics are sort of dismissed because I cannot do these things in such a language. Java is problematic from that perspective, and if I'm writing Julia, picking that up, it's problematic. I know Go started out without templates. They're now doing templates, but more C++ style templates than type-safe templates. I think it's going to punish them because they are not flying in the way they could. They are sort of hovering over the ground, but not taking off. I think this type-safe generics is really dramatically improving the way we can write code, because we can focus on the abstractions we need when we write them, and then we can instantiate it to something useful.
But isn't this also something that C++ people want? Type safety, is that something they can add to the language? Or they have to rewrite the entire language?
In 2009, they were working with the idea of strong concepts. There were two reasons, I think, why that failed. One reason was sort of political, in the sense that if they introduced strong concepts in the library, that would make lots of old code break. And it would require people to annotate their things with strong concepts. And Bjarne Stroustrup was against sort of forcing people to be verbose. The other thing I think was deeply technical, because they tried to shoehorn strong concepts into an idea of inheritance. But if you study the mathematics of concepts, it's different from the mathematics of inheritance. So by shoehorning that, they were sort of getting the first set of examples like semi-group, ring group, field working, but they would not be able to extend it to other combinations of things. So that's sort of a deeper technical reason that their ideas were sort of not really consistent with the mathematics of what they were trying to achieve. But then they sort of killed it because of the divergence. Should you force people to annotate things with concepts, or should you sort of let all the old code run without annotations and trying to automatically reduce some type safety? There were other technical reasons inside this, because they were thinking about concepts which actually don't work, but intuitively it was a good idea because the SDL had done something like that with template trickery and lots of technical details going on. Now, 10 years after they killed strong concepts, they actually needed about a year to rewrite the standard because they had inserted it sort of everywhere. They are reintroducing concepts, but that's weak concepts which only check instantiations and not the template body. And without checking the template body, you cannot be certainly working in your DSL. And we don't get all these benefits, but we get instantiation benefits if the weak concept actually matches what is inside the body. But if the body doesn't match the weak template, there's no support from the compiler, which means that you're at an expert level where you really debug your template body with other means to see that it actually matches your concept. So I think this is a much more user-friendly template mechanism because you get the normal type errors, other errors. You don't need to debug templates using advanced techniques before you can publish them. So I think C++ templates are either very simplistic or simplistic like in the collections library, or they are for experts. They're not sort of tuned in such a way that everybody can easily make them. Simple uses, yes, what we did 20 years ago with core and free numerics, yes, it worked out fine because we were in a simple setting. Not sort of these more advanced things, getting the extra type safety. What I think is that when Fortran publishes this, the C++ people will have to find a way of reacting to this, because they have been reacting to developments in other languages for a long time, like other languages have reacted to developments in C++. So you can sort of see Java pinging off C++, C++ pinging off Rust. So they're everybody trying to sort of integrate good ideas into their language. Now, type-safe templates is going to challenge C++ on the template mechanism. Yeah.
Perhaps a very simple question. So then, you don't get something like header files. So when I see a templated C++ code, then so typically I look at the .c or .cpp file, and these get more and more primitive, and a lot of what I perceive as the proper code moves into the header files. And personally, I struggle with that a bit. So and here in Fortran there's nothing like that. It will sort of be in the .f 2005 or .f 2028 file, or we get the header files.
F90 because it's free form versus F77, which is this form. when I talk to Fortran people, that's the two distinctions they make. No, it should sort of be in the Fortran module system and should behave like modules and be used like modules.
So if I get somebody else's code which I want to study or I have to study, and then I would just study the .f
Yes.
files.
Yes.
Not
As far as I can see, it will be put inside the quick. Yeah, inside the .f file. There should be. It will import requirements from elsewhere, I think, but again, those will be in another module.
Yeah, okay, that is something I'm ordinary use statement.
Yes.
You might have the module defined in different source.
Yes,
This is something else.
but it will follow the module system. It's a block inside a module. Well, the reason we simplify the files in C++ is that we kind of pre-process it and pre-compile it because every instantiation is new, sort of a dynamic linking problem. Here you have all the information, so in principle, the compiler can look at the template and then generate sort of intermediate representation of it. You might want to postpone some optimizations because once you know more about how you want to instantiate it, you can do better optimization than at the general level. But again, we'll look at some techniques for that tomorrow.
A follow-up technical question. Would one be able to distribute the templates in a library as a binary file, or does one have to distribute the template source codes?
If we can distribute things as binary, I think that will be up to how the compiler vendors figure out how they can do it. We've talked lots about name mangling, which would be sort of in the binaries, and then the linker would solve certain issues. So that seems to indicate that it would be possible to distribute templates in a binary format. Because the compiler compiles everything, it understands the template body, it can compile that into instantiation ready code.
But then in the binary, you would provide a certain set of supported types. And if you want to use the template library for your homegrown data type.
No, the binary would have to have hooks for all the template arguments.
Okay.
But the body of the template can be compiled because you understand what functions are being called inside the body with respect to the parameter list. The requirements will have to be visible, but the template body itself does not have to be visible.
Okay. The questioner thanks, very good.
Okay, great.
So it seems we hit the question.
Okay, and now it's about time to take a break. Should we start at 9 o'clock tomorrow, or is 8:30 sort of hard coded?
Because we have to run early to catch the plane back south, I would be a bit reluctant to